Students, today we are going to discuss two more applications of Gauss's theorem. One is electric field intensity just outside a charged conductor. You can see here is a charged conductor in which positive charge is given. Let P be a point near the conductor where electric field intensity is to calculate. Now we are drawing a cylindrical Gaussian surface as shown in the figure. We have already discussed the properties of Gaussian surface. So the flux through the Gaussian cylindrical surface phi E is surface integral of E dot dA. E is the intensity and dA is the area vector. In this figure you can see the direction of E vector and dA vector are same. So we can say angle between E vector and dA vector is 0 degree. So electric flux equal to E dA cos 0 degree, which is E dA. So E kept outside the surface integral dA. So phi E equal to EA. Now according to Gauss's law, we can say phi E equal to Q by epsilon naught. If we consider sigma is the surface charge density, then the charge which is present within the area A is given by Q equal to sigma A. So phi E equal to sigma A by epsilon 0. Now this is equation 1, this is equation 2. If we equate 1 and 2, then we are getting EA equal to sigma A by epsilon naught. Cancel A, so E equal to sigma by epsilon naught. This is valid for a large conducting sheet of finite thickness also. You can see in this diagram, this is a large conducting sheet having some thickness. This thick plate can be considered as the combination of two thin plates, 1 and 2. This side is one plate, this side is other plate. The magnitude of field E1 at P due to sheet 1 is given by E1 equal to sigma by 2 epsilon 0, which is away from E1, and E2 at P due to sheet 2 is given by E2 equal to sigma by 2 epsilon naught, that is also away from sheet 2. Since the direction of both the intensities are same, hence the resultant intensity at the required point is given by E equal to E1 plus E2. Adding we get sigma by 2 epsilon naught plus sigma by 2 epsilon naught. The result is sigma by epsilon naught. If the conductor were negatively charged, E would be directed towards the conductor, because in that case this charges will be negative and E1 and E2 will reverse their direction. Now we discuss the second application, electric field due to uniformly charged thin spherical cell. You see, this is on a spherical cell of radius capital R, and suppose P is a point at a distance small r from the center of the sphere. Taking R as radius, draw a Gaussian spherical surface. Now consider the area vector dA around P. Then the flux through the area element dA is given by d phi equal to E dot dA. Since the direction of E vector and dA vector are same, so it is E dA cos 0 degree, which is equal to E dA. So the flux through the entire Gaussian surface is given by phi E equal to sigma d phi E, that is surface integral E dA. This is it is integration surface integral d phi, which is equal to surface integral E dA equal to E surface integral dA, which is E into 4 pi r square. Now according to Gauss's theorem, we know flux is equal to Q by epsilon 0. If we consider sigma as surface charge density, then we can say Q equal to sigma into 4 pi r square. So phi is equal to sigma into 4 pi r square by epsilon 0. Now if you equate 1 and 2, we get E into 4 pi r square equal to sigma into 4 pi r square by epsilon naught. Cancel 4 pi, so we get E equal to sigma capital R square by epsilon naught small r square. Now at the surface, we get small r equal to capital R. So capital E equal to sigma by epsilon 0. Now at the internal point, if you want to calculate the electric field intensity, say at P dashed, then the Gaussian surface does not enclose any charge in this case, because the charge is on the surface of the sphere of radius capital R. So we write E into 4 pi small r square equal to phi E, which is equal to 0, because Q is 0 in this case. So E equal to 0. So we conclude the electric field intensity is 0 everywhere inside the charged conductor. Now on the basis of above three equations, we can say electric field outside the spherical shell is inversely proportional to r square. Electric field on the surface is sigma by epsilon naught, and electric field inside the surface is 0. The variation of electric field capital E of a uniformly charged spherical shell with distance small r from the center of the shell is shown in the figure. Here you can see this y-axis represent electric field, x-axis represent distance. So at a distance small r, we are getting the value of electric field maximum, which is sigma by epsilon naught, and as you go away from this surface, then this condition satisfied, that is electric field E is inversely proportional to r square.